Okay, sweet.
All right. Yeah, let's get started. Okay. Hi, I'm Andrew Chin.
I'm Christina, and we're part of Vulcan Robotics. Welcome to part 2 of the Vulcan Robotics speaker series. We're here with Elliot, Naomi, and Alex from Robotics, a student-organized, competitive robotics team based at UC Santa Cruz.
Do you want to start with the first question?
Yeah, sure. Can you all give us a brief intro about who you are, your current year in university, and your role in Robotics?
Sure, I'll start. So my name is Elliot Octel. I am a third-year robotics engineering major at UC Santa Cruz. I am the president of Robotics and also the electrical lead of the MATE competition team that we have.
Nice.
Should I also do the icebreakers?
I think we're just going to go through the intros for everybody first.
Sounds good.
We can go to the icebreakers, yeah. Alex?
All right, sure. Hi, I'm Alex. I am a senior at UCSC, and I am the software lead for MATE in Robotics.
Nice. And Naomi?
Hi, I'm a third year at UCSC, and I'm majoring in robotics engineering, and I'm the mechanical lead for Robotics.
Cool. Yeah, so just for kind of an icebreaker question, what's your guys' favorite form of caffeine? Like energy drinks, tea, coffee?
I don't know if we have an order. I think that personally, tea for me. Tea or coffee, really. I don't drink energy drinks all that much.
Yeah, nice.
That's funny. We have a member on our team who half his blood is just energy drinks.
Okay, more than one member, by the way.
Oh, that's true. Yeah.
We have 3 caffeine fiends.
we have those too. Personally, I'm actually a no caffeine person. I think the most caffeine I ever have is chocolate.
Wow. Okay. Yeah, I was a no caffeine person for a while too, but then I've started
You've given in
by the caffeine fiends.
I really love coffee, and it's not even for the caffeine. I just love the way it tastes.
Yeah, same.
I have to limit myself, because otherwise I'll just I'll have a heart attack or something. I drink a lot of coffee.
What's your favorite type of coffee?
I don't really know, honestly. I just kind of go to the dining hall and drink all their coffee.
Yeah, that's fair. Nice.
Do you have a favorite song or artist?
Yes, but I don't like to give out my music preferences all that often, because they're a little extreme.
Maybe we could do some genres or anything that you're comfortable with.
I mostly listen to metal.
Nice.
Heavy metal, so.
Nice.
Do you recommend any bands?
Do you listen?
I've only listened to Megadeth, and that's it.
Okay, if you're looking in the vein of Megadeth, then I would probably go around obviously Metallica and Iron Maiden and stuff like that. If you want to branch out a little bit more, let me just look at my library here. I got Spotify on the second monitor.
Nice.
Really pulling up the preferences. I don't know, you might try some power metal. One of my favorite bands is Blind Guardian. They're good. Or Halloween and stuff like that. If you want to jump far off the deep end, you can try Lorna Shore. They had a new album released end of last year. I will stop there. I will continue talking about that.
Nice. Anyone else?
Yeah, I also have Spotify open on the other screen. Let's see, my top last year was EDM artist, Overwork. Nice. Has some good stuff. Let's see. I listen to a lot of sort of EDM and alt rock.
Ooh,
nice.
What that would be called?
Nice. Any alt rock specific artists?
CJ Goods counts as alt rock. I have no idea what genres I actually listen to. My playlists go great distraction, bopping commute, the spook, and smoothie. So I don't have genres. I have whatever those are.
That's me too.
Yeah.
I don't have like dedicated playlists for like each genre. It's just all compiled.
Mm-hmm. Naomi, any music recommendations?
I've been listening to Grimes a lot lately.
Ooh, nice.
Yeah, that's pretty much it.
Fair. Grimes is very good. As students interested / majoring in engineering, how are you guys liking UCSC?
UCSC is pretty solid. There are some very experienced professors. There are some mediocre professors, but the good ones are always quite good.
Nice.
And the campus, very nice. I will say, until recently, we were kind of lacking in actual making space. We just opened a makerspace, which is very exciting. So we actually have that now, which is good and should help our team a lot. But yeah, overall, the environment's really nice. It's really chill, so students are not really competitive with each other. Everyone's pretty friendly. Everyone's willing to help each other out, which is a really nice environment, I think.
Nice.
Helps a lot with reducing some of the stress of heavy engineering classes.
Yeah. I feel like the engineering space, at least in high school, is pretty stressful. Like, I don't know. It's like the FTC teams that we talk to, it's always like, oh my God, we spent like the whole last week like sleeping in the garage. I'm like, Jesus Christ, that's, yeah, hopefully it's not always like that.
It depends on what you're doing. Definitely not always like that, but if you're working on a project, late nights do happen, but it's definitely important to be healthy about how you do that, because too many late nights in a row and it can be bad for the rest of your life.
Yeah, for sure.
Yeah, I mean, I'd have to agree with Elliot. It's not like UCSC is not the worst school for engineering for sure. Obviously not the best either, but it's pretty adequate. I mean, like you said, we got our makerspace now, although it's not entirely open. Or no, actually, the actual makerspace is open.
The space is open now.
Yeah, that's
People
open
are being trained right
open
now.
to the public, right? So that's pretty good in general. And then like, I've been pretty content with the CS classes. Obviously, you always have your bad professor like every so often, but that's university for you, I guess.
Anything to add about like mechanical engineering, Naomi, at UCSC?
There is no mechanical engineering degree.
Oh, that's unlucky.
Actually, I kind of like that. So the robotics, well, I wish there was a mechanical engineering degree. That'd be great. But I like that the robotics engineering degree at UCSC is more similar to a computer engineering degree, because at a lot of institutions, it's actually kind of like an add-on to a mechanical engineering degree. So I like that it's different at UCSC.
Could you explain a bit about May and how your season schedule is structured?
Sure. Should I do that?
Yeah, I think you're most fit.
Sure. Okay, so the way MATE works is, coming from a first robotics perspective, it's basically the water game that you never get in first. So every year they'll release a new series of challenges to do in I think it's half Olympic sized pool. I don't remember the exact size of the pool, but you have to have your robot rated to 15 meters of depth. You have to be able to control it in the water. The only real restrictions they have are you get more points if you're lighter. So there's a weight limit. Well, there's not a weight limit, but there's low weight bonus. You have to use their power supply. You cannot have batteries on board for safety. So they're giving you 48 volts, maximum 30 amps. You're limited to that. That's the power you get to set to the robot. And that's about it, other than just like safety stuff. So it's really, really flexible in terms of what you actually do with that. And basically, they just have a series of challenges. Things like they'll have PVC structures in the water that you have to go over, take pictures of, do photogrammetry, pick things up, move things around. Some of the things are autonomous. Some of the things can be teleoperated, and they change it around each year to make it new and interesting. So that's the competition. Then the season structure. So they release it about January-ish each year. It's not a set date, as far as I can tell, but it's pretty close to around then. And then the actual event that we do is in May. So we have most of 1.5 quarters in order to actually build the robot from scratch.
Nice.
I'm curious, how many iterations have you guys had for your robot?
This is either version, I think this is year 5, version 4, because COVID year, I think, we kept the same robot and tried to modify it for the next year. So I think we're on version 5.
Yeah, because the COVID years, they just extended the tournament.
Yeah, so I think this is robot 5.
Nice.
Yeah. We are currently building the robot, so most of the electrical parts are in. Mechanical is going to start manufacturing this or next weekend. Software is upgrading our code so that it supports the slightly different layout that we have for this year.
That actually leads very well into my next question. So, the water is obviously a very big factor to consider when you guys are building the robots. Obviously, you can't have electrical on the outside like we do in FTC. So, how do you take it into consideration when designing the robot?
I guess this is my question again.
That's for you and Naomi for sure, yeah.
Yeah, okay. So I'll start with the electrical side. So yeah, water is very much a factor in the design of this. Last year's robot actually died because of the water. It had a leak, and it died because of that, because we could not get the right part to resolve the leak in time. So yeah, we have the main way that we keep our electronics out of the water is we have an onboard enclosure. It's just a box that seals IP68, waterproof. IP ratings are a bit weird. 6.8 is not always fully waterproof. That's the depth that we want, so we have to be careful in that, which is kind of annoying. There's not a good rating for, it'll survive 50 meters of depth. There's a rating for, it'll survive a meter of depth, and then we just find one that's actually rated deeper. But yeah, so we have most of the electronics are just inside the enclosure. They have to be waterproof because they're in there. And then to actually get to them, we have things called penetrators, where you make a hole and this thing bolts on either side of it with a watertight seal and allows wires to pass through. Mm-hmm. And then our thrusters, our motors are specifically underwater thrusters, so they're brushless motors that are perfectly fine being in the water because they're fully sealed.
Nice.
Yeah, now each have things add.
From the mechanical point of view, we have to take into account a lot of the materials. So we work with materials that are inherently waterproof, like we 3D print with PETG, and we do a lot of CNC routing with HDPE. And these materials are also pretty much neutrally buoyant, so we don't have to worry a lot about buoyancy calculations. We also the mechanical team has to do the waterproofing for the electronics. So anything that goes outside of the enclosure has to be encased in epoxy in a special type of box that we have to design. Usually we custom make those boxes and then 3D print them and then encase things in epoxy. We sometimes do fluid simulations of things to see how they'll react in the water, like on the thruster guards and on our claw. We've done that. We tried to do that this year, but our SolidWorks license wasn't working properly. So, yeah. But yeah, we've done that in the past. Yeah, that's pretty much it for mechanical.
Yeah, so you guys also answered my next question was which was about custom parts. So when you guys so you guys do use custom parts, right? And yeah, we also used custom parts for our FTC bot this year, but we had some difficulty waiting for there's long waits for the CNC stuff. So how do you guys deal with the waiting parts for custom parts?
Yeah, so custom is definitely there are two main ways to do custom. There's in-house and there's getting someone else to do it for you and then ship it into you. And so for us, we are lucky enough to have access to an in-house CNC. So we've pretty much just designed as much as we can to be in-house manufacturable for mate. Usually that's basically everything except the PCBs. And PCBs have a very long shipping time because they're the only way to affordably make PCBs is to get them made in China and then shipped in 2 or 3 weeks. So that's just a matter of really good time management, so you have enough time to actually get the PCBs in, test them, and if you need another round, be able to actually order them and still be able to make it within the deadline. But Naomi, I think you can talk a bit more about the actual in-house manufacturing side.
Yeah, so we do pretty much only CNC routing and 3D printing. And I don't think we've ever actually had a part that we ordered because it takes a long time and it's expensive, and we have the tools to just make it ourselves. So we just do pretty much everything in-house.
Nice.
How long does it usually take for you guys to make stuff in-house? Like, can you guys give us an example about a certain part and how long it would take to make?
Yeah, sure. So for the thruster guards, we 3D print those, and those typically take about like 10 hours to print on the 3D printer for both parts, the front and the back. And then for the frame, we cut those out on the CNC router out of sheets of HDPE, and that can take quite a long time on the router, depending on whether the router is working or not. But putting out each piece usually takes anywhere from 30 minutes to 2 hours. So in total, it's about like 5 to 8 hours for the entire frame.
For this season, we've had some issues with like managing all the parts and all the prints because like we need to account for all the time, and then we run behind, and it's just a mess.
Yeah, we've had a lot of breakdowns with our 3D printers. So, yeah.
Yeah, we are no strangers to broken 3D printers. I think of the 4 printers that we're using right now, one of them is currently out of commission until we can get a new PTFE tube for it, and another one was potentially broken, but then someone was able to fix it, so it's fine now.
We have like 3, and then I think 2 of them are working, and then one of them is just not extruding, and we can't get it to work.
What printers?
Huh?
What brand?
Oh, Prusa Mini.
Oh, hey, that's what we have.
Oh, nice.
Yeah.
Nice.
Yeah, not extruding. Check for a clogged nozzle. Check if the heat break has somehow lowered down too far, because those can sometimes lower down and they'll get stuck.
We've used like an acupuncture needle to just jam it up the nozzle and see if it's like if it'll do anything.
Yeah.
No luck so
So that
far.
would help with the clog, but you should check the actual position of the tube inside of the heat break.
Okay.
Because sometimes it can fall down. I know that happened to one of ours once.
Thanks for the advice. Could you give us a rundown of your team's past competitions, like the structure, how you guys managed it?
So because of COVID, none of us here have actually been to a competition because it was held virtually when we were here. So we don't know what the in-person competitions are like. That said, from my understanding, I believe the process is we go to the place this year. It's in Colorado. They have a interview portion where they do basically just a technical interview, asking you a bunch of questions about your design of your bot, why you did certain things, all of that sort of thing. And that's some portion of the points. Then there's the actual demonstration where you go into the pool, you have a set amount of time, and you have to do as many tasks as you can. You get points for the ones you complete. And I think there's also some points given based on your documentation, because there is a pretty big documentation portion of this competition where we actually have to write out a technical document of different parts of the robot, why we designed them the way they did, what things we built, what things we bought off the shelf, why we bought things off the shelf, why we made things custom, all of that. And all those come together to form all the points. And then at the end of the competition, it's based on who has the most points as to who places what. So it's a lot less, there's no head-on-head in Mate compared to FRC where you are literally just playing sports.
Yeah, can you do a breakdown of your current robot design with all your major subsystems?
Yeah, sure. Do we want to do per sub-team?
Yeah, that would be great.
If that works.
We should start with that. Naomi, do you want to start with the mechanical side?
Sure, I can start. So on the mechanical side, we have the frame of the ROV, which is pretty much the superstructure that we have made out of HDPE. And then we also have the thrusters and I guess you could include the cameras sort of, because we make the pop boxes for those, but those kind of are also electrical. And then mechanical is also in charge of the manipulator mechanism, which this year we were trying to make a robotic arm with servos and 3D printing.
Yeah. So then electrical's job is just to integrate to make those parts work. So we've got the main microcontroller on board, which is just an Arduino. It was an Arduino Mega last year. This year we might be able to get away with an Arduino Uno, just because we don't need as many PWM pins, because we're doing a slightly different strategy for how we're controlling everything. So the Arduino sits in the middle. It has an Ethernet shield so that we can communicate with the surface. A laptop on the surface is what does the heavy computing, so it's what's doing the actual autonomous processing and everything. And it just, since we're powered by a tether anyway, we might as well do all the processing on the surface and not rely on power on board. So we send the 48 volts down onto the RV. Some of that goes to power the Arduino. The rest of it is voltage divided via some pretty beefy buck converters into 12 volts, 5 volts, and I think it's 42 volts that the lights are using this year. So the lights are being run off the 42 volts, and they're being dimmed by the Arduino. Each light is a ring around each of the cameras. There are 4 cameras. Each of the cameras is a USB camera that goes into a hub, which also goes up to the computer. The thrusters, we have 7 of them this year. Each of those control is brushless, so they're controlled by brushless motor controllers, which are then controlled by the Arduino and powered by a 12-volt supply, dropped down from the 48. And let's see. And then for the servos, you're going to be creating a custom shield for the Arduino, which will just run each of these servos in the arm. And I believe that's the system. Oh, there's obviously the safety precautions on the surface, so we have an emergency power switch and a fuse, just so it doesn't, like, kill someone if it shorts.
Oh,
Nice.
For software, Elliot's kind of explained most of the electrical portions, but basically top side we have the laptop, like you said, and on that laptop is running a cute GUI app that will take in like an Xbox controller's inputs and convert those into, currently we just have it like a string of PWM values. We are looking to maybe turn that into like a JSON file that gets sent down an Ethernet cord all the way down to the Arduino, where it is then parsed by some code on the Arduino and turned into actual PWM outputs that go to each of the motors. And then obviously, since we have our servos and the lights now, we have to add, those little, we have to add both the inputs and the actual outputs. So yeah, it's also going to be controlled by said controller on board. And then obviously we have the cameras as well. The GUI application handles those as well. So top side we have a little screen that shows all the cameras. We can switch between them depending on what we need to look at, obviously. And yeah, from there we are able to do our autonomous processing, which may end up being like outsourced to a little command line application rather than being done purely through the GUI. I believe that's about it for software, unless someone reminds me of something I've forgotten. But yeah, it's actually not super complicated. Only a couple systems working together.
I'm curious about the kill switch that Elliot mentioned. Do you just find out where water's leaking from?
It's a physical switch.
Oh, so like you turn it off manually?
Yeah. No, it's just an actual switch. We just sourced a very high amperage switch that can handle the 30 amps. So it's on the surface, and if we notice something wrong, we can hit that.
Oh.
Or in line, in series with it, is a fuse, a 30 amp fuse. So if something goes wrong on the bot and it shorts, that short will draw more than 30 amps, and that'll just cut the fuse automatically.
Got it.
Yeah, I'm also curious about the Ethernet cable. Is the Ethernet cable constantly connected to the like how would it connect to the robot while it's moving around?
It's very long.
Very long.
50-foot tether.
Is there like usually outlets near the pool that's like for the Ethernet?
No, the Ethernet directly plugs into our computer.
Oh, yeah. Okay, that makes a lot of sense. Nice.
Yeah, and then we have waterproof connections on the bot, so it's a special Ethernet connector that can handle being underwater.
What's the challenge your teams face when it comes to building the bot, and what lessons have you learned from it?
Water.
Water is, yes. Water has killed so many things. Yeah, it just makes testing more annoying. It makes just everything more annoying because you have to have basically everything done in order to put it in the water and test it. Because you have to physically drill holes in the enclosure to run cables, so all the cables have to be run and waterproofed before you can put it in the water and test it. Yeah, so that does bottleneck the testing a bit, and then that just means that we have to spend a lot of time just figuring out how to make those connections waterproof without spending absurd amounts of money, because waterproof penerators can become very expensive. Power connectors especially have been a challenge because a lot of the power connectors that handle 30 amps are like $500. And no, thank you.
Yeah. So what do you guys like practice with the robot? Is it like, do you guys use the school's pool, or like?
We do not use the school's pool. They would not be happy with us doing that.
Fair enough.
This year it's your pool, right, Naomi?
Oh, nice.
Yeah, so I wasn't here for this year, but at the very first year of our team, we did try to use the school's pool, and we got banned from the pool.
Oh, no.
So ever since then, we've been trying to we kind of just beg people to let us use their pool to film our video. And this year, though, I finally have a pool at my house, so we can use the pool.
Nice. How many breaks do you guys, like, just an estimate, how many breaks do you guys get from the water, like, this season?
It's usually just one, because, if you break the robot with water, it's kind of catastrophic.
Yes, so, well, the issue with that is it was breaking it on the day of competition, and the way that it was doing it was leaking through one of the penetrators that we had, and the only way to get a replacement penetrator was to order it, and it would not have come in time. So that was a fatal break. Yeah, the unfortunate thing is because this is a very high-risk environment that we're operating in, if something goes wrong, like a good 50% of the things that could go wrong just take us out of the competition entirely. So we have to do a lot of testing beforehand, ideally, to just make it so that everything that breaks before we put in the water. And then once it's in the water, everything's well soldered, everything's well screwed down, bolted down, carefully set, so that the only things that could possibly go wrong are maybe a little bit of software that we can change on the fly. Worst case. But yeah, no, it's a very testing heavy competition in order to actually make sure that we can't break, because we can't afford to break.
We experienced something similar, like not the same degree, because ours isn't in water, but we always get all of our breaks like the day before competition, and then they just stay overnight and try to like test everything. Like you said, make sure it breaks before we actually put it on the game field.
Yeah, because once you're in a game field, you can't pull it off to fix it.
Yeah. What does the average day in the workshop / garage look like for you guys? What do you guys usually work on? Is there like a schedule?
Yeah, so Robotics, because it is a multi-project team, each of the projects has sort of times that they reserve to use our space. And partly because we're moving spaces right now, it's a bit weird in terms of where we're currently meeting. We're meeting in like a conference room on the 5th floor of the engineering building, because not everyone has been actually cleared to work in the new lab. So probably in the next month we'll be all working in that new lab space, and that'll be a lot nicer. But for right now, every weekend we meet for 2 hours. All 3 of our sub-teams meet at the same time, so we can coordinate, talk to each other about things. And it's pretty much just everyone shows up. We start with a bit of a meeting just to make sure everyone's on the same page, and then go off to work on our sub-things. And then us 3 sub-team leads sort of make sure that everyone within our sub-team sort of knows what they're doing. And from there, everyone's sort of in their own little groups working on the one subsystem that they're doing at that moment.
How does the coordination process go? For us, it's sometimes very hard for people to align their schedules to come in at the same time.
Yes.
Do you guys have like
Any tips?
weekly Zoom meetings or any like surveys or something?
Yeah, we survey at the start of the quarter, basically put out when to meet as to when people are available to meet. And then because we're only meeting for a couple hours each week, because that's all that college students can really afford, we just find sections of time when most people are available. And usually everyone is able to go, except maybe one person might not be available for one weekend and can Zoom in, and then we'll just make Zoom available. The good news about being a university that just went through the pandemic is that most of the rooms are equipped with TVs that have a camera on the top of them, so you can Zoom into it. So that is a benefit, that it is possible to technically work remotely.
Nice.
Yeah.
So they're kind of like a robotic version of themselves, just like you wheel them around the workshop.
No, the TV's bolted to the wall, so they're just looking out over the room.
Nice. So they're like an overseer. That's cool.
Software mostly spends its time working on the GUI and the Arduino, although now we have a new little PWM board that we have to get working so we can use the Arduino Uno and actually control all the servos, all the motors, and all the lights from one Arduino, because otherwise we wouldn't have actually enough PWM pins, even on a Mega. So yeah, that's about all we do.
Do you guys have any like team bonding events, like outside of like pure robotics sciencey stuff?
Yes, we bash things in fires.
Oh,
Like a rage room?
No, we have what we call slugventures, and quite often these are either bonfires at the beach, or we go and hang out at some location. I don't know what we've done in the past. I only know, like the last ones I've been to were bonfires.
Yeah, bonfire has been the most repeated one.
Yeah, and at our last one, we did a little bit of caveman engineering in our bonfire.
Nice. What you guys do? Like, did you?
We split a log in half with another log.
Nice.
oh, we should do something like that. That'd be fun.
And then we learned after the fact that firewood or using beech wood as firewood is a bad idea because the salt produces carcinogenic smoke.
Oh,
so
lucky.
Don't do that.
Bring your own firewood. That's a safety warning. Do you guys have any general advice for high schoolers looking to pursue a major in engineering?
Yes, we do. But am I starting again?
Anybody can pop in. Whoever wants to go can go.
Sure, I'm starting again. Okay. So let's see. First off, so in your college career, you're going to have your classes. Those are going to give you sort of the basic knowledge on the theory of all the things. You'll get the math, you'll get the physics, the sciences. If you're in electrical or robotics or something like that, then you'll get the electrical theory, you'll get the controls theory, you'll get statics, mechanics, things like those. And that's a really good base. But one, you shouldn't limit yourself to that. And two, do not be afraid to start learning those things before those classes. So you'll learn those, and every other student in engineering is going to learn those. So if you want to actually stand out, and if you want to really develop your skills, you're going to want to also be doing other things outside of that. Now, it's pretty flexible what you do with that. You could be joining a club like Robotics, where you just hands-on make things, learn how to do things, and that's a really good complement to your more structured, more just theory-based education. You can do personal projects, just making things in your spare time. That's a really good avenue, especially if there are specific things you're interested in. Like if you want to learn how to make a graphical interface for a clock, then you can go buy a little Arduino kit, buy a screen, and make that graphical interface for a clock. Or if you're like, it'd be really cool if I had a keyboard with a couple extra buttons that could do this. You can get a USB-enabled microcontroller like a Arduino Pro Mini or a Raspberry Pi Pico or something like that. Get some keys, make a little board, and program it to be that. And that's a really good thing to do just to sort of practice on your own. Let's see. And then as high schoolers, before college, you can do those things before college. Yes, yeah. It's just good to keep trying things out, keep learning things. Like, yeah, if you like engineering, if you like that kind of thing, it's good to do it because the only way you can learn is by actually practicing.
It sounds like you guys have all done some like personal projects in the past. Do you guys mind sharing some of those like personal or like outside of robotics, outside of school, engineering projects you've guys done?
I have a ton that I've started and then never finished.
That's fair.
So yeah, I can't really talk about a lot. It's a lot of very like beginning projects, but they were fun to learn the concepts from. Like they were fun to explore. Like I tried once making a QR code generator. Turns out QR codes are very, very complicated and involve a lot of linear algebra that I didn't really want to do. And also the specifications are behind a paywall. So,
Oh, no. Okay.
yeah.
Damn.
Couldn't do that one. I tried making an emulator once. That one's still technically in progress. But I was also trying to learn a new coding language while doing it. If you've ever played around with Rust, you know that it's not a ton of fun, unless you're a masochist somehow. I don't know. People who do Rust like professionally are insane, I think. I did not enjoy it. That's also on pause. I don't have a ton of personal projects myself. It's mostly stuff I've done in class.
Yeah, it sounds like there's a lot of ambitious stuff. I feel like all engineering students have that same things. Like, you always want to make stuff, but you never really have the opportunity to finish a project.
Yeah, I always go here when I should probably try to go for something over here. You know.
Anybody else want to share like some personal projects or experiences with projects just in general?
Okay, I mean, the last personal project I did was in high school, but I made like a little box that played a song because I was in orchestra, and it was kind of a joke because I always played this one song over and over. So I made a little like black box that if you like pressed a button, it would play the song.
That's actually, yeah, that's so cool. I was in band as well, and we've had a senior do a similar thing. He had this little music box that he would bring along at the end of the last school year. It was like, let me just bring it to band class. Yeah.
I do have some advice for high schoolers who want to major in engineering in college, and I would say do some rigorous research on the programs you are applying to. So I would look into the actual professors there and see if you're interested in their research. Also research what people say about the professors and the classes at your school. And there are always going to be some bad reviews, but like see if people think, oh, this is really easy, oh, this is way too hard, and see if it's the kind of environment you want to get into. Also see if there are good resources to help you during your tenure at the school, how advising is, and that kind of thing, to make sure you're getting into a program that you actually will enjoy and succeed in.
Good advice, yeah. What would you guys say is like the biggest challenge you guys had for each subsystem?
Waterproofing, probably the overarching biggest one. And under that, because we're in such a tight space and have such limits on that sort of thing, actual power density and just being able to route all the power to each individual thing inside of a very small enclosure was a challenge that we are still grappling with right now. Just making sure, so we have all the parts, we have the enclosure, we have to fit everything in there and connect all the high power wires, which are pretty thick wires, to get to every single part, and make sure nothing shorts in this very tight space that need to be able to have waterproof underwater. So it's very hard to spread things out.
Yeah, I'd imagine it'd be kind of hard to like jam your hands in and try to like connect all those things. Well, it's just like a tiny box that's supposed to swim, right?
So yeah, that integration is definitely a challenge.
Software's biggest problem is probably that computer vision is really hard. Because we're in charge of like the autonomous tasks and stuff. So we've been going around and looking for, because currently this year we have to create a 3D model of an object that's in the water, which is already kind of tricky, but we also have to measure both the size of the object and then also like the area of patches on it. So that's already like a really tricky problem for us. But we're currently looking for like frameworks that'll allow us to actually create a model, or ways for us to use like OpenCV. I don't know if you guys have worked with it or anything like that. No, we're basically trying to either like make the model ourselves or find something that will make the model for us. But then we still have to measure all these spots and stuff. Ironically, what our GUI does, because it was written by some people who were in the team before like I became the lead and all that. Figuring out what the GUI and how all that works was easier than all of this, despite the fact that they didn't comment anything. So yeah, definitely our computer vision.
For mechanical, I think a big problem is always CAD doesn't always look like the real thing.
Oh, yeah.
So like last year we had a penetrator, this massive penetrator that didn't get onto the CAD, and so we had to cut out a huge chunk of the ROV with like a Dremel. Yeah, that was fantastic. So every year we have to make sure that the CAD fully matches the ROV so we don't have those little errors that really cause a big problem.
I hate CAD sometimes. Like, every time something prints, you just have to modify it over and over again with, like, the drill or, like, with the bandsaw or something. And it's just like, if you just fixed it in CAD, then we wouldn't have to spend all this effort. It's really annoying.
Yeah. We had a 4-bar mechanism for a robot this year, and I spent almost 2 hours sitting down to put the servos in, and I was like, dude, this is like, why didn't we just print this out or just re-CAD it? But yeah, it's difficult sometimes.
Back in my FRC days, I remember our 4-bar mechanism for a climbing mechanism, and it worked perfectly until it actually was trying to lift a robot, and then there was just this one tiny little edge that would cut the rope every single time. So yeah, those little things will kill you.
Yeah.
Software's biggest problem is probably that computer vision is really hard. Because we're in charge of like the autonomous tasks and stuff. So we've been going around and looking for, because currently this year we have to create a 3D model of an object that's in the water, which is already kind of tricky, but we also have to measure both the size of the object and then also like the area of patches on it. So that's already like a really tricky problem for us. But we're currently looking for like frameworks that'll allow us to actually create a model, or ways for us to use like OpenCV. I don't know if you guys have worked with it or anything like that. No, okay. So we're basically trying to either like make the model ourselves or find something that will make the model for us. But then we still have to measure all these spots and stuff. Ironically, figured out what our GUI does because it was written by some people who were in the team before like I became the lead and all that. Figuring out what the GUI and how all that works was easier than all of this, despite the fact that they didn't comment anything. So yeah, definitely our computer vision.
For mechanical, I think a big problem is always CAD doesn't always look like the real thing.
Oh, yeah.
So like last year we had a penetrator, this massive penetrator that didn't get onto the CAD, and so we had to cut out a huge chunk of the ROV with like a Dremel. Yeah, that was fantastic. So every year we have to make sure that the CAD fully matches the ROV so we don't have those little errors that really cause a big problem.
I hate CAD sometimes. Like, every time something prints, you just have to modify it over and over again with, like, the drill or, like, with the bandsaw or something. And it's just like, if you just fixed it in CAD, then we wouldn't have to spend all this effort. It's really annoying.
Yeah. We had a 4-bar mechanism for a robot this year, and I spent almost 2 hours sitting down to put the servos in, and I was like, dude, this is like, why didn't we just print this out or just re-CAD it? But yeah, it's difficult sometimes.
Back in my FRC days, I remember our 4-bar mechanism for a climbing mechanism, and it worked perfectly until it actually was trying to lift a robot, and then there was just this one tiny little edge that would cut the rope every single time. So yeah, those little things will kill you.
Yeah. That wraps up our questions for today. If you want to see more about Robotics, you can find all their socials on their website or in the description below. Subscribe for more content and follow our socials too. thanks for coming and doing this interview with us.
Thank you.
Thank you.
Bye.
Thanks for having us.
Thank you.